semantics of Grainless. So first of all, Prakash, since I get to go second, then I figured nobody else would have a chance to show the photographs that I found on the internet yet, so I get to go first. So congratulations, Prakash. It's not the years in your life, it's the life in your years that count. I'm sure you remember those days.
I do. Barely.
That was before I met you.
Is he smoking something? Finest tobacco.
Okay. So many congratulations for your 60th birthday. It's been a privilege to have you as a friend and a colleague over the years. And as Prakash reminded me yesterday, he's even stayed at my house and showed my kids his wicked backhand slice on the table tennis table. Keep up the great work.
Thank you.
And here he also wins badminton tournaments. So the type, maybe I should just use this. This talks about denotational semantics of shared memory programs. And it's pretty much a historic retrospective, putting my more recent work into historic perspective. And actually Prakash plays a role in this too. And I've tailored this talk to deal with essentially partial correctness and race freedom. But the work does extend, as I'll say at the end. I'm going to point out some of the major issues that arose in his semantic design historically, and there's still an issue now. And those main issues have to do with fairness, granularity, and race conditions. And the basic theme of this talk is developing a truly grainless model, what that means, and why I claim it matters. So just to remind you, the kind of shared memory programs we're talking about here, imagine processes running concurrently on a shared state. So those processes can read and write to shared memory. And they use synchronization to ensure mutually exclusive access on critical data, so you don't get any confusion about what the intended state is. And here's a simple example programming language to support this. The details are not relevant. I'm not going to go into much detail about the semantics anyway, just on the general level. But in this language you can see, for example, we've got the usual imperative sequential constructs like assignment, sequencing, conditionals, and loops. We've also got a synchronization construct, which in this specific language is a conditional critical region with R when B do C. R there ranges over a set of what are called resource names, which behave like binary semaphores. And then finally we've got C1 parallel C2. So in the traditional semantics for this kind of language, it goes back all the way to David Park. The meaning of a program is typically taken to be a set of traces, where the traces are sequences of steps, and each step represents the effect of an atomic action by the program on the state. So I've sketched at the bottom of there using some Greek letters and funky notation, the general structure there. So states are functions and variables. I'm assuming that they're integer value variables. Steps are pairs of states. And traces are finite sequences of steps. Actually, finite or infinite sequences of steps. That is the infinity there. And the meaning of C is a trace set. So actually, the domain we're working with here is the power set of lambda to the infinity or inclusion. And David Park gave a classic paper where he gave a model of this nature to the very programming language that I'm talking about. And his development introduced some fundamental key ideas that have been relevant ever since in giving models to similar languages. In particular, Park modeled sequential composition, C1 semicolon C2, as concatenation of traces from trace sets. He modeled parallel composition as fair interleaving of traces. And another notion that goes along with this is the idea that a trace with what we call only trivial gaps are executable. I'll explain what that means in a second. So some of the traces of a program are executable. Some of the traces in the traces of a program are not executable, because you can't get from the beginning of the trace to the end without assuming some interaction from the environment to change the state at midpoint. But you need to include those non-executable traces in the trace set of a program if you want to get a compositional semantics. This is well known. For example, even though for C1 semicolon C2, concatenation is a very well-behaved operator on trace sets. I don't know why there's an extra space there now. Somehow you've inserted extra space. Parallel compositions got very wide. The traces of C1 parallel C2 are the interleavings of traces of C1 with traces of C2, but the executable traces of C1 parallel C2 cannot be determined just from the executable traces of C1 and the executable traces of C2. Because when you execute the two things in parallel, sometimes C2 can fill the gaps that C1 has in its traces and result in an executable interleaving. This is well known, goes back, I think, to Milner. So fairness, as Park introduced it in giving his semantics, is a crucial assumption if you want to use the semantics for liveness analysis. Well, that's actually not so relevant today when I'm talking about partial correctness, but it's still relevant in the background. And Park gave a characterization of what he called a fair merge relation on traces. Park characterized the relation fair merge, which was a subset of power set of lambda to the infinity cubed, triples of traces. Alpha, beta, gamma is in fair merge if gamma is a fair interleaving of all of alpha with all of beta. And he gave a definition of that relation in the domain theoretic setting as a combination of least and greatest fixed points used in a nested way. It's rather awkward to use that. Later I showed that you could characterize it more simply as a greatest fixed point in a more flexible way. And again, those details are not so relevant to today's talk because I'm talking about finite traces. And finite traces interleaving is very straightforward. But fair execution is inherently linked semantically to unbounded non-determinism. If you're assuming fairness, you're just assuming essentially that if processes haven't yet finished, they'll eventually get given a chance to run for an unspecified amount of time. But that basically means that if you're saying, I want my semantics to make sense for arbitrary fair executions, then there's a potential there for unbounded non-determinism, depending on how the scheduling is chosen. Well, guess what? Prakash is involved in the early development of this theory. Prakash, in fact, developed some fundamental connections between fairness and non-determinism. So on this slide, I've got a summary of 3 of Prakash's papers. Read this very quickly. But the main point is that he's done a lot of fundamental work here. The paper in 1984 on semantics of networks containing indeterminate operators, that was actually presented at the seminar on concurrency that Glenn and Bill Roscoe and I organized in Pittsburgh. That was the first time I met Prakash. He's also done work on non-expressibility of fairness and signaling, and the expressive power of indeterminate data flow primitives. So these are, I might say, from Prakash's classic period. I looked these things up on ACM Digital, the ACM Digital archive, and I found this. I thought you'd find this amusing. That's the bibliometrics of Prakash's publication history on the ACM. The point is his papers are widely cited. For example, he's got available for download 12. There were 245 downloads in the last 12 months and 5,895 downloads cumulatively. And I assume those were not all just his grad students doing it. Or his parents. The only thing is Prakash hasn't yet provided any contact information on the ACMs. So in particular, I think we should choose a photograph for him, maybe that one.
Where are you finding these photographs?
Your Facebook page is very helpful. Okay, so what's granularity? Well, the traditional models, going back to Park, assumed a fixed notion of granularity or atomicity. And that means that they assume that certain units of program action are executed indivisibly. And the semantics is actually constructed in a way that makes that obvious. And in Park's model, for example, assignments were atomic action, were treated as semantically atomic. And also evaluation of Boolean expressions was an atomic action. And typically, and this still makes sense, it makes sense to assume that actions that involve synchronization are indeed atomic. So acquiring a semaphore, flipping the value of the semaphore so nobody else can acquire it, that has to be assumed to be atomic. Okay? So these traditional models assumed a fixed notion of granularity, and there's more than one choice that makes sense. So it's actually just as reasonable to assume that assignments are not atomic, but reads and writes are. So when you do an assignment, you read the expression on the right, evaluate the expression on the right, and then you do the update. It makes sense to separate those two actions. So in general, once you fix a notion of granularity, you can get a notion of partial correctness behavior for programs based on the traces you get that build in that particular atomicity. So once you've done that, you can say that the partial correctness behavior of program C is determined from its finite executable traces. So a finite trace looks like that. It's executable if and only if each step, the state you get to is the same as the state you begin from in the step afterwards. Okay? That means you can get from the first state to the last state just by performing actions of the program without needing to assume that the environment does anything else in parallel. And then you say the behavior of C is the set of sigma sigma prime such that there's a trace alpha of C that leads from sigma to sigma prime in the obvious way. Just chaining the states together. I don't know why all my spacing's gone different here. That arrow alpha is further to the right on my arrows. Somebody in Oxford doesn't like my LaTeX. So, here are the semantic definitions, for example, if you want to specify that an assignment is atomic or reads and writes are atomic. The details again are not important, but the point is if assignments are atomic, then the traces of an assignment are singletons, the traces with one step. And if reads and writes are atomic, I've given a definition there where the traces of an assignment have two steps. There's a read step and a write step. Okay? The details again are not crucial. But whatever you do, you have to fix the level of granularity if you're doing it this way. And the behavior, the partial correctness behavior of a program is sensitive to granularity. For example, if we look at the program there where we've got two parallel increments to x, and we start from the state in which the value of x is 0, the final value of x depends on whether you're assuming that assignments are atomic or whether you're assuming that reads and writes are atomic. If assignments are atomic, then the final value of x has to be 2. But if reads and writes are atomic, x can be 1 or 2 afterwards, depending on how the reads and writes get interleaved. And this is really annoying. So the point about this is that's a racy program. It's a program in which there's a concurrent write to x. So I'm not being politically correct here using words like racism or whatever. That's a racy program. One process writes to a variable that's read or written by another in a way that influences what the other one does. And the point is the behavior of a racy program can depend on granularity, hence on scheduling all of it. This is all well known, this is just history. So a solution to this that was proposed in about 76, I think it was, Wiki-Greece logic, was to impose syntactic constraints on program structure so that you could only prove the correctness of programs that had no races. And then you could still use a granular semantic model where you choose a specific notion of atomicity, and the logic doesn't care about race conditions anyway.
Steve, you said syntactic, but is your math?
I said static constraints. I said syntactic, which means the same as static. But the problem with that approach, and that does give rise to a logic, and that logic actually is still relevant nowadays because it's related to more recent developments such as concurrent separation logic. But that approach does not extend to more modern languages that include mutable state, like separation logic. So that approach is fundamentally limited by the imposition of static syntactic constraints on programs. And the reason it doesn't extend, of course, is because when you've got pointers there, you can't detect agency of the pointers on the basis of purely syntactic properties. You need to do evaluation as well. So along the way, two fundamental principles got enunciated, not necessarily in this order actually. Dijkstra's principle came first. But Reynolds' principle was that potential race conditions in a program should be modeled semantically as a catastrophe. Because there's something bad about race conditions. It leads to behavior that's flaky, depends on scheduling. We can't hope to reason about all possible behaviors of a program that has a race condition. So we should treat it semantically as a catastrophe. Dijkstra's principle, on the other hand, which is actually the principle behind the Wiki-Greece logic, is that we should be able to regard processes as independent, except at the infrequent places where they synchronize. That's actually not, it's both a principle and a guiding light in how to design concurrent programs. Dijkstra called it loose coupling. So a program is loosely coupled if the processes only interact infrequently. Okay, so these two principles actually appear to be in tension with each other, because a race condition is not a local property. It requires you to look at least two threads to figure out whether there's a race condition. And if you're doing that, how can you be treating the processes independently? So there's an apparent tension between these two principles. But what I claim is that we can incorporate both principles at the same time if we do it carefully enough. So that my thesis is that we can design a race-sensitive trace semantic. So this is a version of trace semantics that evolved from Park's early models. Park's early models didn't say anything about race conditions. It didn't deal with them at all. It had a fixed notion of granularity. We can design a new version of trace semantics that's race-sensitive, and it embodies both of those principles. So race conditions show up in the trace structure as traces that have a race at the end of them. And between synchronizations, along the traces you see actions, steps. Some of those steps involve synchronizations. Between successive synchronizations, what we're going to do is completely abstract away from what happens step by step. The big step in between synchronizations. And by abstracting away from what happens in between synchronizations, that's how we ignore granularity. If you think about it in the example of assignment versus reads and writes being atomic, if you have a two-step trace that does a read followed by a write, and you abstract away from what happens intermediately, you get a one-step trace that does the read and write simultaneously. And that's not the full story, but that's part of it. And the key thing here is that the race-sensitive behavior of a program suitably defined. So if there's a race, you get top rather than a final state. That notion is independent of granularity. Not just for assignments, but for full programs in the language. So this is the key observation. We can distinguish between between racy programs and race-free programs in a way that's independent of granularity assumptions. For example, C is race-free from a given state sigma. There's no execution of C that leads to a race condition that's enabled from state sigma. If you assume that assignments are atomic, if and only if the same property holds for C and sigma, assuming that reads and writes are atomic. And it's also if and only if any other choice of atomicity. Okay. So the advantages of doing it this way is that we end up with a semantics, a trace semantics, which is independent of granularity, unlike Park's original models. And the only atomicity assumptions that are still left is that synchronization primitives, like acquiring a lock and releasing a lock, are atomic. And I think those assumptions are still reasonable because you have to have some key, simple notion of atomicity built into your implementation if you're going to ensure mutual exclusion properly. So all I'm assuming is that semaphore operations, binary semaphore operations, acquiring and releasing a lock, are atomic. And that's built into the semantics. For a race-free program, its behavior, its race-free behavior, is the same as its old unrace-free behavior in the previous definition, because the top never shows up. And it's true for all granular models have the same. For a race-free program, for a race-free program, in every granular model, it has the same meaning anyway. It's only for racy programs where you get these unwanted differences. And by abstracting away from the internal order of actions between synchronizations, this is a key point as well. By doing that abstraction, you end up with a trace set that's much more succinct. And by doing that, we can try to tame the combinatorial explosion. When you do interleavings of long traces, you get long interleavings, large numbers of long interleavings. If the traces have bigger steps, the interleavings tend to be shorter and the trace sets tend to be more concise. So the slogan is fewer traces, shorter traces, bigger steps. So here's the traditional scene. In the traditional scene with Park's trace semantics, you fix a definition of what's atomic, for instance, atomic assignment. And that induces a definition of behavior, assuming atomic assignment. The trace semantics is compositional because it includes non-executable traces, but the behavior of a parallel program, basically the executable traces, isn't compositional. So you need a compositional model to reason about this in a syntax-directed way. But the bad thing is that if you choose a different notion of atomicity, you get a notion of behavior that's not the same. Okay? So what happens when you do it my way is that we end up with a grainless trace semantics that's an abstraction of all of these specific granularity models. If you ignore granularity by doing what I call maximal mumbling in between synchronizations, you end up with one grainless semantics that abstracts away from all of those. It's still compositional, and it induces a notion of race-sensitive behavior. And for raceless programs without races, the behavior up there is the same as it used to be in the old, in any of those models in Park's tree. So the key fact is the different granular models at Park's level yield the same grainless model by doing this construction. Executable granular traces yield executable grainless traces and vice versa. The executable traces in the grainless model come from executable granular traces. And if C is racy from sigma, then that shows up in the race-sensitive behavior in that way. There's a sigma top entry in the behavior of C. Okay. So the key ideas here is in this newer construction, is that traces are no longer sequences of steps, where steps are pairs of global states. Essentially, the states in Park's traces represent global states, the entire shared state. My traces are sequences of what I call footsteps, and a footstep is a pair of states again, but the two states represent the reads and the writes that are done in a finite number of atomic actions by the program. And we don't care about what order the actions occurred in, all we care is the overall reads and writes. So we call that a footprint of the sequence of actions the program does between synchronizations. And we need to define ways of combining footprints in ways that make sense to deal with sequential composition and parallel composition. And there are some straightforward ways to define partial operations, taking two footprints which are composable in sequence and building the footprint that represents doing them in sequence. And taking two footprints that are executable concurrently and building the footprint that represents doing them concurrently. And also detecting a race if there is one. So in the semantic construction, which I'm not going to go into detail since I've only got 5 minutes left, and I wasn't planning to anyway. In the construction, we construct traces using these partial operations for combining footprints, not just concatenation and interleaving, but taking account of these gluing together operations on footprints at the same time. And we only construct what I call the relevant traces. A trace, I'd say, is relevant if you can use it to build an executable trace of the program by finding a suitable way to interleave it with another trace. So here's a technical definition. Alpha is a relevant trace if there are traces beta and gamma, such that there's a way to merge alpha and beta together and get a race-free trace gamma that's executable. The details are not crucial here, but the point is it's fairly easy to give a semantic characterization of which traces are relevant to constructing the executable traces of a parallel program. And you can do this in a compositional way. This also corresponds to a structural property of alpha. Just looking at how alpha is laid out in between synchronizations is the local property of alpha alone. So the point is that relevant traces of C can be defined in a way that's compositional. And we can use what I call maximal mumbling to abstract away from the internal sequencing of what happens in between synchronization steps at the same time when we do this construction. So basically the slogan here is grainless equals relevance plus mumbling. Very memorable phrase, I'm sure you'll remember that. I tend to mumble a lot, so as you all know.
That's not relevant.
Not usually maximal. So when you do this, you end up with the trace semantics in which the finite traces look like this. The typical trace has a sequence of resource actions, like acquiring a lock and releasing a lock, interspersed with footprint steps. And actually these steps are also footprints, but they're footprints involving semaphore variables, not program variables. Okay? And the gaps in these traces, for example, from here to here, allow for the possibility that the environment interferes. And the key point here again is that if the environment is, if you have a trace like this, and there's a resource action there, allows for the possibility that the environment might be using a resource in a way that changes the state between there and there, and that's okay. But if the environment tries to change the variable the program is using without acquiring a lock first, it will be a race condition, and that will be detected in the interleaving construction. So there's no loss of generality here about, by abstracting away from what happens in between synchronizations, because we're doing race detection, we've lost no generality. So the conclusions, In contrast with the Park-style semantics that I began this talk with, in the grainless trace semantics, the states that appear in the traces are what I call local rather than global. We just talk about the piece of state that the program itself currently needs to use, what it's reading and what it's writing, rather than saying the global state. A step in a trace is an abstract record of the effect of a sequence of atomic actions, which is a much more longer phrase than what we use to describe Park semantics. In Park semantics, a step was the effect of a single atomic action, and you had to say what was atomic. Now we've abstracted away from that. And then using race detection and mumbling in the way I've indicated, it gives us a model that's independent of granularity. So one semantics fits all in a sense. And fair merge lives on. I'm still using Park's fair merge operation in this construction. I guess I already clicked the next slide. So here's my attempt to justify why grainlessness is important, is relevant. So grainlessness actually is an implicit property, I think, in traditional semantic accounts of sequential programs. When you say the meaning of a sequential program is a partial function from states to states, you say a state is a mapping from variables to values. You don't say a state is a mapping from variables to sequences of words at the machine level that contain integers stored in 32-bit words or whatever. Nobody in their right mind would use the semantics at the word level to talk about the meaning of why Hall logic is sound, for example, for integer-based programs. We typically say, well, it's enough to assume that we've got an abstract notion of state. But you can prove that it doesn't matter. If you gave a concrete model of state and used it to give us semantics for sequential programs, it's not difficult to prove that Hall logic is sound with respect to a concrete model or an abstract model. By proving a theorem that says that what happens at the abstract level is faithful to what happens at the concrete level. And that's true for a whole range of implementations based on very simple general assumptions. But we don't do that. I think everybody probably assumes automatically that it's okay to work with abstract models of state. So what I'm trying to show here is it's also possible to do this for concurrency, where it's not so obvious, and where behavior the behavior of a concurrent program can be sensitive to what's happening at the machine level. But for raceless programs, race-free programs, the behavior shouldn't depend on the implementation, and a grainless model like this brings that out in a clear way. So our aim is to establish analogous results to that for concurrent programs, shared memory programs. Oops, and I've got plans to do some more work on this in the future, but for some reason I got. Did you have a little button there that you pressed to open the trapdoor on the stage? Exit the slides. So I'm going to try and apply these ideas in further settings, for example, to deal with things like weak memory models, and also to deal with total correctness and safety and liveness properties. You just need to go back into the semantic model and add the infinite traces back in, and that can be done. But I thought for the purposes of this shorter talk, I'd just omit those details. And also I think I can develop some extensions of separation logic to continue this line of work. Similar models to the one I'm describing here have been used to show the soundness, for example, of concurrent separation logic, and also permissions logic in similar design principles. Great. Thanks very much.
So this one-size-fits-all slogan, is that some kind of universal property of this grainless semantics? Is it like the most abstract?
Yes, it isn't.
Compositional?
It isn't yet, but I'd like to try and prove something like that. Yeah. So it's possible. I haven't finished trying to figure out whether it really is fully abstract, the notion of behavior that's implicit here. But I think it probably is. It's the closest I've ever got to it, so I'm hoping it is.
I seem to recall Peter Hearn talking about algorithms which are deliberately racy and cleverly exploiting the particular granularity. So are you kind of saying that those are bad algorithms?
No, I'm saying they're not bad algorithms, but if you have a model that deliberately exploits raciness, then it presumably has a built-in notion of atomicity, so you would want a granular model.
Okay.
Reason about that.
Okay.